Dr. Mona M Salem
Is it clear
from
now?
Faculty of Architectural Design and Built
Great,
Environment,
great.
Beirut Arab University,
Thank
and
you.
my colleague Dr. Rami Musa from Faculty of Computer Science and Artificial Intelligence, Paris University in Alexandria. One of the challenges facing creating smart buildings with respect to climate change is achieving thermal comfort inside the building in addition to conserving energy during use. Smart educational buildings are considered one of the most systems that need thermal comfort during the presence of workers and students, which helps to study and focus better. These smart buildings need advanced systems to monitor the change in physical properties that affect the thermal comfort inside the building. Physical properties such as temperature, humidity, air velocity, and carbon dioxide ratio are among the most important factors that affect thermal comfort and energy conservation in smart buildings. The use of IoT devices, which is already supported by sensors to measure changes in these factors inside buildings, has become a necessity, as it can collect a lot of information throughout the day and during periods of temperature and energy usage peak. Managing this huge amount of data is one of the most important requirements in order to reach the optimal use of energy and achieve thermal comfort within smart buildings. Thus, the aim of our study is to combine two different models, the physics-based model and machine learning. As for the physics-based model, modeling and forecasting the dynamics of multi-physics and multi-scale systems remains an open scientific problem. Besides, physics-based modeling algorithms require significant computing resources and not suitable for fast prediction. On the other side, for machine learning, is considered as one of the best ways to manage complex processes and link different physical variables in order to help make a decision to achieve indoor thermal comfort. This study focused on design and optimized thermal comfort model in educational buildings based on IoT monitoring sensors and hybrid parameters of the physics based on XGBoost machine learning model. Structure of the model. The hybrid model consists of the physics-based and machine learning parts. By integrating these two parts, the developed model is able to take both advantages of the physics-based method and machine learning method. The studied dataset was taken from the indoor monitoring system containing IoT sensors. The system offers an inexpensive way of monitoring the indoor environment with Wi-Fi sensors able to make real-time monitoring of temperature, humidity, CO2, air velocity, room occupancy, and light levels. The dataset collected every minute during educational day in 8 hours for 3 selected variables. The monitoring system was installed in the walls of the classroom. The duplicates were first isolated from the dataset. The procedure of duplicates removal was performed with the use of Python 3.10.5. The 9 wall-mounted IoT devices are used in order to provide real-time information about different parameters that affect indoor thermal comfort in educational buildings, as shown in Figure 2. The data processed are gathered through 3 layers as follows. Layer number 1, perception layer. In this layer, the IoT sensor can record the information about indoor humidity, temperature, and air velocity. Layer number 2, network layer. The gateway devices are responsible for data routing from the previous layer. Number 3, cloud layer. In this layer, the data was collected and the analysis would take place. The aggregated data that's stored in this layer is real-time monitoring data. The visualization and the statistics would help in taking the best decisions through the statistics provided from this layer. XGBoost is a type of machine learning algorithm that's used as a supervised learning technique due to its efficiency and faster learning process through an ensemble algorithm based on gradient boosted trees. XGBoost integrates predictions of weak classifier tree model to achieve a strong classifier tree model via a serial training process. It can provide overfitting by adding a regularization term. Parallel and distributed computing makes the clearing process faster to give a quicker modeling process. Figure 3 shows a schematic diagram of the computational process of XG. In this study, the XG post algorithm was ran in Mathematica Wolfram 13.1 software. Well, the computational process of XG post appeared in the process is calculated by equation number 1. For the XG post algorithm, post steps and number of fields are important parameters. The problem of finding the optimal algorithm was changed into finding a new classifier that can reduce the loss function with the target loss function shown in equation number 2. Substituting equation 1 into equation 2 and then following some deduction steps, equation 3 could be obtained. The final target loss function was then converted into equation number 4, and the model was then trained according to this target loss function. Now, how can we validate our model? We use these two equations. Equation number 6, normalized mean bias error, and equation number 7, the coefficient of variation of the root mean square error. These two equations are used as a validation matrix to evaluate the accuracy of the XG post model. The physics-based model convention results in Figure 4 shows a change in indoor temperature and relative humidity during the period between March 2021 and October 2021 in the educational building. Temperature increases and reaches the maximum level at the top. In Table 1, the two parameters and evaluation metrics from the XG post model are presented after construction. According to the results shown in the Table 1 and Figure 5, it's clear that hybrid model maintains a relative reduction in errors, with a slight change in the results between the two models, in a faster processing time for the arithmetic operations than traditional models. And finally, in Figure 5, it shows the true value x-axis versus the projected value y-axis plot for optimized XG posts with high accuracy. So, conclusion. An optimized model consists of two sections, an application of physics-based model for prediction of thermal comfort, and a hybrid integrated model for thermal comfort real-time calculations using IoT devices within an educational building using XG-boost algorithms can monitor the indoor thermal comfort values. So the results show that the model can accurately predict the indoor environmental parameters. As well, the error measurements in the three variables was below 5% for temperature, below 6% for relative humidity, and below 9% for air velocity, with very low computational time. This indicates that the hybrid model could be an effective one to help the end user in decision making. Thank you.